So let's talk about how we can actually increase trust in our explanations. So first of all, I would like to understand the aspects that undermines users' trust in an explanation, and then we're discussing one very specific approach for diagnosing the potential trust one could have in these explanations. So let's start with motivation and important properties. If local explanation should not only make a model interpretable, but also reveal if the model is trustworthy, right? That is very important. If we're getting local explanations but can't trust the model in the first place, so what's the reason that? So how does it really play together, right? So interpreted question often includes something like, why did the model came up with the decision? For trustworthy, however, we're saying how certain is that explanation, right? So do we trust actually explanation we coming up from using a certain technique on a model? So first of all, of course, we'd like to have accurate insights into the inner working of our model. However, there's also the failure case attached to it. We generate our local explanation based on inputs and areas where the model was maybe not trained with, so we had there little or no training data at all. So we had to extrapolate actually into regions which were quite unlikely that this really makes a sense or was not really intended for the model to be trained on anyway, right? So if that's happening, and we discussed it, for example, in the context of Lyme, we have a potential problem already. The second point is robustness, so that means low variance in our explanations, of course. So we're saying that similar explanations for similar data points should have again similar predictions, right? So if that's really true, that would be very nice and desirable actually from a customer perspective. However, we have multiple sources of uncertainty in here because, we sample quite a lot, and based on maybe how we sample, how we have distance matrices and so on, we have maybe different kind of outcomes. So we would like to measure how robust an IML method is to change small changes in the input data or our parameters maybe of the model. And then, of course, is an observation again out of distribution or not, right? If we fail in any of these, that could undermine users' trust in the explanations, and that again means if we don't trust actually the explanations, maybe we're also not trusting the underlying model anymore, right? So that's again these interplay of things. Let's talk about out of distribution detections. So we have seen already that models are unreliable in areas with the data support, right? So if extrapolation can't be really guaranteed in the first place, right? Some models are a bit better in exploration than others, but in general, we don't have data really if you're going out of distribution completely, so we can't guarantee too much there. Nevertheless, if we're now using an local explanation method, sampling out of distribution, we might ask the model to give us predictions, which, as I said, are not reliable. So for local explanation methods, we have seen that already, that they could do that actually, so really going out of distribution in the following case. So the data we sampling for generating the Lyme surrogate model could use out of distribution data. Counterfactuals themselves could be out of distribution, right? Going too far from the point X we'd like to explain, we could maybe end in certain regions which are out of distribution. If we talk about Shapley values, we permute the observations to break up more than the correlations between features and so on. Then we could go out of distribution. And even for ice curves, for sampling the grid data points to generating the ice curve, no one is really saying that these are in distribution, so it could be in out of distribution. There could be two very simple and intuitive approaches for tackling that. First of all, as we try to classify for out of distribution, and the other one is we try to come up for clustering, also saying, okay, what is our area, what is our part of our space where we believe in this we could call the in distribution. Of course, we could go much more complex and then that, variational autoencoders and so on. There are many techniques actually. So all these kind of ideas with one class classification and so on, or detecting outliers goes in a very similar direction actually. So let's say we're using an out-of-distribution classifier, we train that. The problem is we only have in-distribution data from our training data, right? So we don't have out-of-distribution data. If you would have these kind of data, then it would be in distribution already because we're using everything we have for training our model in the first place. So the idea could be to hallucinate new data, which is of course an out-of-distribution, by randomly sampling data and checking actually these, right? Then we could simply learn a binary classifier to distinguish between the origins of the data. So this is in distribution, so coming from our original training data, or these from this randomly sampled point somewhere. There's also a study whether an explanation approach can be fooled. We talked already about that briefly. So the question is, if we have these kind of classifiers, can we now hide a bias in our model by first classifying actually whether a point is in distribution or out of distribution, and then using that to fool more or less our explanations. And that's actually an important way not to attack directly our explanation, but also to diagnose actually whether our explanation technique is very robust and it's doing what it should do actually. Okay, let's talk briefly about an approach where we're using clustering, and here the idea would be to use dbScan. It's a very famous and traditional approach actually from the 90s. And that really goes in the direction of spatial clustering with a density-based approach. The idea is we have a certain amount of points, which we call simply x. We have n of these, and we're saying we have a neighborhood around our points, and that's called an epsilon neighborhood. So epsilon defines simply how large our neighborhood is, and saying simply for each of our points we have, there is an epsilon distance more or less around that. So if xi is at most epsilon away, then we would put it into our set of epsilon neighborhood points, right? D is simply a distance measure, as always, could be Euclidean or Gower distance, whatnot. The core observation are of course x, and we're saying that it's really core, so it's really essential for being in distribution if our data point x has at least m data points from our original training data within these epsilon neighborhood, right? So there's more you can see, it's not on the border of our distribution, but it's really quite in the middle of our distribution, and we have many points around that. Yeah, I forgot to say that of course then forms an own cluster with all its neighborhood points, right? So we always say core observations forming a cluster within its epsilon neighborhood. Then what we also have are border points. So these are of course not core observations. So they have less than m data points within their epsilon neighborhood, but are nevertheless within the epsilon neighborhood of some other core point. Right? So they're part of a cluster defined by a core point. And then we're saying there are also some noise points actually, which are not within an epsilon neighborhood of any of the clusters from the core points, right? So they are maybe fairly far apart. You can say, yeah, somehow we sampled these, but you know, maybe by chance actually are not really belonging to our original distributions. They're very unlikely that we see them, or maybe are only due to noise. So here's visualization for that. What we can see here is that the green points A and B, so here and there, these are core points, because we're assuming here that m, the number of points in the neighborhood, has to be 4. And that's simply check that it's true for the point A. So A is of course in its own neighborhood. The point C over here is in it, B is in the neighborhood, and that one, right? You have then 4 points in the neighborhood. And the same applies actually also for the point B. So we have B itself, we have A and these 2 points in there, right? If we now consider, for example, I don't know, that point C over here, right? That would be the neighborhood of C. Only C itself is in there and A is in there, but nothing else. So it's not a core point, it's a border point, because it has not these 4 points in its own neighbor. Point D actually is not belonging to any of the clusters. So if we're checking the, was here the green one, green border, right? You see that D doesn't belong to any of these clusters. So D has to be then by definition a noise point. Okay, so also now written up in the slide. So D is a noise point. And now we can say what is actually in distribution, what not. So everything which belongs actually then, as I said, which falls to that region. Okay, so the disadvantage of that is that depending on the distance metric, D, right, we need to define for our epsilon neighborhood, DBs could suffer from the curse of dimensionality simply. So really have to think about how to define D and also what kind of features we'd like to choose. Also then, of course, based on epsilon and based on the number of points, your clustering could be completely different, right? So if you would increase epsilon slightly, for example here, now D would fall into it, right? Could even mean that if we increasing epsilon slightly for that point, so it was before was that line, right? So now going a bit bigger. For that point, we have that point, that point, that point, that point in here. So right now it happens now that that becomes a core point, so the cluster region is actually increasing. So same, of course, if you're changing M, also the number of core points will change. If we decrease M, the number of core points increases. So really, depending on these 2 very important hyperparameters, your clustering will change quite a bit, and it's not obvious how to set them. Okay, let's talk about robustness a bit more. So we would like to differentiate between different kinds of uncertainty we have with our explanations. So the explanation uncertainty refers to the change of explanation if you repeat the process. Right? So it could, for example, include that the explanation could differ depending on which subset of the data we use for the explanation. Right, so what kind of points you sampled, whether you use some kind of the training points and how we sample these, and of course also which hyperparameters they used, right? So think about Lyme, for example, we're using some kind of a surrogate model. The surrogate model itself, of course, has hyperparameters. How complex do we create the decision tree or your linear model? What kind of, I don't know, what kind of regularization we're using maybe for our linear model. All of these will really impact what kind of explanation you will get. But there's also not only the explanation uncertainty, but in addition, the process uncertainty. The change of explanation here then means if the underlying model is changed. So not the explanation model, but really the underlying machine learning model. So if we slightly change that because there's some noise in the data and we sample it maybe slightly different, how much will the explanation change? And of course, we would hope that also the explanation is fairly robust to that, but of course it depends also a bit on how robust your underlying target model is actually. We focus a bit on the former part of the explanation uncertainty and go a bit more in that direction in the next slide. How could we actually now measure this kind of robustness? And there's actually one way of doing that. So the goal here is that we would like to have similar explanation for similar inputs, right? So if they are in a very close neighborhood, we would expect, yeah, the explanation should not change too much. For Lyme and CHAP now, we have a notion of stability based on a locally Lipschitz continuity. And that was shown in 2018. The local Lipschitz is simply saying that for every point x0 in our feature space. And let's say that x0 is not too far away actually from our point x we'd like to explain. So it's only a delta part away of that. It implies that we can now bound how much the prediction of x and x0 is far away based on how far x0 is away by some factor omega. So it can't be arbitrarily far away, but it's now bounded actually by that omega. So according to this, we can now quantify the robustness of the explanation models in terms of omega, right? So we would like that that's not too far. So we're saying that if omega is very small, that is even stronger bounded, right? So that also means then the robustness of our explanation model is even better. Unfortunately, that omega is not really known a priori again, but nevertheless we could somehow estimate that, and we're doing that by going over all points in the neighborhood of the point x we'd like to explain. We have an A2 loss now on the explanations again, G, right? So how much the labels, the predictions of G given xi will change with respect to G of x. And we normalize that by the distance simply, right? So simply saying here, we put that in proportion to each other, and that gives us more or less than something like an omega value for how good it is.